Hi, today's notes are on 8.5, Sums of Infinite Geometric Series. So if you watch the video that I posted, you'll see that there are certain types of series where the number starts to reach, like when you add it up, the partial sum may approaches a limiting value. So the first n terms is called a partial sum. Okay. And let's try to bring this into a little bit of context. So let's imagine you've got your square from the video, and the first thing we do is we have half of it. So we've got this half colored, right? And then what we'll do is then we'll add a second half, and then, a quarter, and then half of that quarter, which is an eighth, and then a 16th, and then, right, a 1/32, 1/64, and you can see that eventually this entire square is going to be filled in, or at least it looks like it. But if I zoom in, the pattern's going to continue forever. So this partial sum is basically saying that we are going to, let's see what it approaches, even though here I proved it. So if I take like 1/2, S of 1 is the sum of one number. Okay, S of 2 is the sum of first two numbers, right? So it'll be 1/2 plus 1/4. And this is approximately, actually, let's do a quick fractions review. You ready? So we'll do 1/2. Sorry guys, I'm a little all over the place right now. Equal, so we'll do 1/2, but we'll make common denominators. So those will be 2/4 plus 1/4 is 3/4, which equals to 0.75. 1/2 is exactly 0.5. Okay, so the sum of three numbers is 1/2 plus 1/4 plus 1/8, right? And so these first two numbers we know is 3/4 plus 1/8. And we can make common denominators. That'll be 6/8 plus 1/8, 7/8. On your calculator, that is 0.88. Okay, so let's keep going. We have 1/2 plus 1/4 plus 1/8 plus 1/16. And so this part right here, that's 7/8 plus 1/16, which is 14/16 plus 1/16, which is approximately 0.94. Okay, so hopefully you're starting to see a pattern, right? So we know that we're going to take all of this plus 1/32, and if you notice the pattern, it's always going to be one short of the denominators, so this is going to be 31/32, which is approximately 0.97. I'm going to ignore the graph right now. Actually, I'll talk about it. You don't need to write this in. So if I use this graph as my x and y axis right here, we'll see that if we have, we'll call this our terms, and this will be out of 1, but we'll count by tenths. And I'll never ask you to do this yourself. This will be 1, 2, 3, 4, 5. And so based on what we found, the sum of one term is 0.5, 0.75, 0.88, 0.94, and then 0.97, and hopefully you can start to see that it starts to curve and this approaches an asymptote at y equals 1. So we can see that S of n, as n gets infinitely bigger, starts to approach 1. Okay, so here I'm going to just take a moment to talk about and like algebraically why this works. So if I take S of n equals to a1, and this is the formula we used yesterday, 1 minus r to the n over 1 minus r. Okay, and let's pretend that we are going to add an infinite number, so S of infinity. Okay, so a1 is 1/2. We have 1 minus 1/2 to the n power. Ooh, but n is infinity. And then we have 1 minus 1/2. Okay, so this equals to, we can rewrite this as one big fraction. So our denominator is 1 minus 1/2, which is just 1/2. I can bump this up on top, and I'll move it here, right? And imagine like our denominator is down here. So then I have 1 minus 1/2 to the infinity power. Well, these two 1/2s cancel out, and we have 1 minus 1/2 to the infinity power. Well, if you guys remember, an exponential decay function looks like this. And as we approach infinity, this function is going to approach 0. So then we have 1 minus 0, which is just 1. Now let's think about this for a second. This works because 1/2, which is an exponential decay function, approaches 0. So this would work as long as it's an exponential decay function. Now let's imagine we're actually adding numbers that keep getting bigger and bigger and bigger. If we add numbers that are going to get bigger and bigger, well then we're going to keep adding more and more numbers, so the number we're going to approach is infinity, not 1. Okay? So therefore, when we have this equation or formula, it has to come with a restriction. This formula only works if r is a fraction between -1 and 1. Okay? So that means it's a decay function. If r is greater than 1, and we have something that looks like this, right? Then the number that we add is going to keep getting bigger and bigger, and so it has no sum or limiting value because the sum approaches infinity, right? So it's not a number. Okay? So find the indicated sum for the geometric sequences. The first thing you want to ask yourself is, does it have a limiting value or not? Okay, because you're 50-50. If it's a decay function, it has a limiting value. If it's greater than 1 and it's a growth, exponential growth, then it has no limiting value. So take a look at this. This is my r is greater than 1. So this function is going to get bigger and bigger and bigger. Therefore, the limiting value or the sum does not exist. The 3 dots is therefore. Okay? This one is r is equal to 1/3, so that's a decay function. Okay? So since it's r is between -1 and 1, then we do have a limiting value, and we can find it now. Okay, so our formula is S equals a1 over 1 minus r. Now this is no more n because n is just infinity now. So we do have to figure out what our first value is. So a1 is 2 times 1/3 to the 1 power, which is 2/3, I believe. And then we have 1 minus 1/3, which means that we have 2/3 over 2/3, both of which cancel out to be 1. Okay, let's practice some problems. So these look slightly different. Okay, we know we're going to be finding the sum because it's adding together. We do have to figure out what it's changing by. And from 20 to 4, I think that it's dividing by 5. So it's 1/5. And we can check on our calculator. 4 divided by 5 is 0.8. Okay. And this one is growing by 3. A multiplier of 3, sorry. Okay. So one of these doesn't have a limiting value. See if you can establish which one you think it is now. R is greater than 1, therefore the sum does not exist. And that means you just don't have to do any more work. Okay. This one is exponential decay, so it does have a limiting value. I'm going to write the formula one more time. And so we know A1 is 20. We know we're going to have a 1 minus, and then 1 over 5. So that means we'll have 20 over 4/5. Sorry. Without pulling your calculator out, we can get rid of the denominator of the fraction. Okay. 5 over 5 is 1, so we can always multiply a fraction's numerator and denominator by the same number. So that gives us 100 over 4, which is 25. Which makes sense. See, we start at 20, then we add 4, and then we add less than 1, less than 1, less than 1, so it starts to approach 25. So how is this applicable? Like, why do we care about a limiting value? Well, let's see this scenario in real life. If we have a pendulum, which is like the clock, right? So like there's that thing that swings in a grandfather clock. It's a pendulum. And if it releases and swings 15 inches on the first swing, there's your A1. On each successive swing, the pendulum travels 75% of the distance of the previous swing. That's my R. What is the total distance a pendulum swings? Okay, so let's confirm. If you hear total distance, that means we want to add it up, right? So that's a sum. So let's write our formula first. We have 15, and then we have 0.75 to the n minus 1. That's a of n. I don't know if I need that yet, but let's take a look. We do need s equals a1 over 1 minus r. Oh no, I just needed to identify a1 and r, right? So we know a1 is 15. We have 1 minus 0.75, which is 15 over 0.25. Please don't take out your calculator to do 15 divided by 0.25. Convert it to a fraction. That's 1/4. And then we can times 4 and times 4 to get a total of 60 inches. Okay, so make sure you catch the units. Okay. This last part we didn't get to in class today, but I'm just going to record the video so I don't have to re-record the whole video next year. What we're going to do at this last part is we're going to write repeated decimals as a fraction. So you guys know on your calculator, say if you did like 2 divided by 3, that you're going to get a number that just continues forever. And this one we recognize, and we know it's 2 divided by 3. But what about some of these that we don't recognize? Okay. So you can actually think of this as a series. Sorry. And what I want you to do is find the repeated portion. So you see how you have like 0.72, 72, 72, right? So we're going to repeat 72. So 0.72, the first one, is our first term. The next part is the number, the next part of the number, 0.0072. Okay, so you see how this plus this is 7272 right now. And then if I add the next 72, 0.000072, and it continues forever. Okay, so how do we find the rate then? Okay, a repeated decimal is going to have a number that you approach. So we know the rate equals your second term divided by your first term, or previous term. Okay, so your term divided by the previous term. And we know that the 7 2's like divide, right? So it's almost like you can cross these out. And you have 0. Oh, actually, I should not do it that way. I'm sorry. Let's not do shortcuts that don't always work. Let's check it on our calculator. Okay. .01. Oh, good thing I didn't just cross things out, right? Okay, so 0.01. Okay, so if my rate is 0.01, we want to find the sum, so we're going to take sum of 0.72 over 1 minus r, which is 0.01. So far, so good? And when we divide this, guys, if we want to, this one we can, right? Because it's the same number of decimals. This one I couldn't because it had different like decimal values. So this is the same as 72 over 99. If you don't trust me, we can confirm, just to make sure I'm not lying to you. Oops, sorry. And then we'll check this, 72 divided by 99. There we go. And we do want to reduce always. I'm not going to say it. Divide by 9, divide by 9, which gives me 8 over 11. Okay, let's do another one, because this is a really weird process if you think about it. Okay, so the repeated number here is 5. So really what we're doing is 0.5 plus 0.05 plus 0.005. 0.0005. Would you guys agree that I'm multiplying by 1 over 10 here, right? Dividing by 10. Okay, so I can use my sum formula, and it's an infinite series. It's a decay function, right? So it is going to approach a value. So let's see. We have a1 is 0.5, and then we have 1 minus 1 over 10, which is, if we wanted to make it simpler, 0.9, right? It'll be 5 over 9. And let's check and just confirm. We can't use our calculator to find the answer, but if we have an answer, we can check that we are correct. Okay? So try the last two, see if you can make that work, and we will check in class.